Hi everyone, this is lecture video 9 and the topic of this lecture is the derivative as a function. As you remember, in the previous lecture video, we defined derivative of a function at a point like this. So we define the first derivative at some particular point by using this limit expression. So we insert this minus f of x0 divided by h. If you take the limit of this ratio, you find the first derivative of the given function at that point. And this limit or the first derivative value has also a geometric meaning. It is the same as the slope. So this is the same as the slope of the tangent line drawn to your surface at the point x equals x0, right? Slope of tangent line to y equals f of x at this special point, okay? Now, we are generalizing this limit definition of the first derivative from a point to the variable x like that. As you can see here, instead of, okay, let me zoom out a bit. Instead of putting a particular point x0, now we are putting the variable of the function x, and then the rest is the same. Then this is now depends on x, right? This expression now depends on x. Because x is not a certain point here. Not a certain point anymore. That's why, in this case, this expression, the result of this limit, is in fact a function depending on x. Okay, so this is the limit definition of the first derivative function. It is a function now. But here, if you insert a certain point for x, for example, x0, you will find a real number, which gives you the slope of the tangent line. But in here, this is the more general case where we give the formal definition of the first derivative function, okay? So this is something important. In fact, the formal definition of the first derivative function. Now, there are also an alternative way to define this limit expression for the first derivative. Okay, I think you remember this picture. There is this second line here, and this expression, this ratio is in fact coming from the slope of the second line. And remember that this was the image of x, and here this will be the image of this point, x plus h, so that, you know, this difference is h. If you solve for h here, okay, so let's zoom in this part. We have x and we have this x plus h point. That's why, okay, this difference here is h. Now we want to call this point as z. You see, we name it as z. So then h is what? H is, in fact, so let me write it in this way. Z equals x plus h, telling you that h is in fact z minus x. That's why if you send h to 0, so you see I am analyzing this behavior here. So if you send h to 0, then what happens to z? Then z has to approach to x. So z goes to x if h goes to 0, obviously. And And so this is the key point of writing this expression which defines the first derivative with a limit. This is the key point for writing this expression in an alternative way. So all you need to notice is that you call this x plus h thing as z. So we have z here. And as h goes to 0 now, for the denominator, what you can write instead of h, you can write z minus x, right? And you also need to transform this part like z goes to x, okay? If h goes to 0, obviously this point goes to and approaches to x. That's why this is the new alternative formula of that definition, okay? And so I can write here again f prime x. So we have two different expressions stating the same thing. Let me put some boxes around them. Just a second, okay. Okay, so I want to emphasize them by putting inside boxes like this. And you know, the derivative function of the derivative of f is defined through this limit. You can either use this version of it with the h, or you can use this version of it with the z notation, okay? And the alternative version is this one. Now let's apply this through an example. Read the question, please. Find the derivative of square root function. So the function is given as the square root. We will find the derivative function of it, okay? So part A, we want to compute this by using the limit definition that we covered here. So I prefer to use this version of it. It is also possible to write in this version. So this is what this is: x plus h minus fx divided by h, and h goes to 0 in the limit. So let's compute this limit. Our function is a certain function, you see, square root of x. How do you evaluate f on x plus h? So obviously you will write limit as h goes to 0, evaluate square root function at this point. So like this, minus then this part is square root of x and this. So what happens to this limit as h goes to 0? If you try to insert 0 for h, you understand that the whole expression behaves like 0 over 0. And in the lecture videos covering the limit content, we learned that you can get rid of this indeterminate form by multiplying and dividing by the conjugate of this part, right? So what I mean is this plus square root of x. This is the conjugate of the expression in the denominator here, and you will divide by it. Multiply and divide. You have to also divide by it, not to change the question, right? Okay, then what happens? Let's see. Limit as h goes to 0. This is now in the form of a minus b, a plus b, and you can multiply them quickly, like a square minus b square, and then at the denominator we have this whole thing, plus square root of x. Okay, now we have simplifications like this, and then we are allowed to simplify h so that we end up with this expression now. X plus h minus square root of x. Okay, if you send h to 0 now, here this part goes to 0, and then you find your result as 1 over 2 square root of x. So you see, by computing this limit, we find, in fact, the first derivative function of square root of x, okay? So the result of this limit gives you what? It is the first derivative function, okay? So maybe I can also emphasize that. If your function is the square root function, then the first derivative function is given as this expression, which we computed by using this limit definition of the first derivative. This is part A. Now look at part B, please. We want to find the tangent line to this curve at the point 4. So our point is here. And at this point, you see, we draw a tangent line, which is drawn in red in the graph. Now we want to find the equation of this line, okay? This red line here is the tangent line to your curve at x equals 4, and we want to find the equation of it. To find the equation of the tangent line at the point, okay, our point is this one, 4, 2. What we need to do, we need the point and we need the slope of this tangent line, right? So you already remember that the slope is given by, the slope, which we denote by m, is at this point is given by the first derivative of the function evaluated at the given point 4. So you see, we have an expression here for the first derivative. That's why we just insert 4 for x for this first derivative expression. So square root 4. That's why the slope is 1/4. Okay, and then by using the point information and the slope information, we can easily write the equation of the tangent line given by y minus y0, and then slope times m times x minus x0, just insert the data you have. So y minus the y component of the point, which is 2, slope is 1/4, then x minus the x component of your point. Okay, this gives you the equation of the desired tangent line in the example. Okay, after covering this example, let me move on with the notations for the first derivative. We already use this notation for the first derivative, and there are also other notations denoting the first derivative function. You can use y prime, or you can use dy over dx, the f over dx, or like this. These are also notations, but they are not that common to use. We will be using most of these notations in our lectures. And you can also denote the first derivative function at the particular point x equals a like this by just inserting x equals a to your notation in the first case. If you want to use this notation, you will draw this line, vertical line, and say x equals a at the bottom, and so on. Okay, these are the different notations that we will be using for the first derivative function. Okay, so look at this part now. In this figure, we will analyze right-hand derivative and left-hand derivative. Okay, this is the same picture that we covered here for defining the first derivative function. And now, what we are going to do is to look at these endpoints of our domain. You see A and B are the domain of our function. B is here. What if we want to compute the first derivative at this left-hand point or at this right-hand point? Keeping in mind that your function is not defined out of this interval. So f is not defined over here, and f is not defined over here. That's why at the endpoints, you need to be careful about this limit. H goes to, instead of h goes to 0, we will say that if you are looking at the derivative of your function at this left-hand point, you see h is bigger than 0, so you can send h to 0 from right direction, okay? So if you are looking at this point, h goes to 0 from right, and if you are interested in the right-hand point, then you send h to 0 from left. Okay, from left. And so this will give you the first derivative of your function at the point A, which is the left-hand point, and the second expression here will give you the first derivative of your function at the point B, which is the right-hand point of your interval. And the results of these limit operations are called as the right-hand derivative at A here and left-hand derivative at B. B point is here. Be careful. If you are at the left-hand point, you need to take the limit as h goes to 0, okay? But from the positive direction. If you are interested in the right-hand point, h should goes to 0 from the negative direction. So like this and this. We are using one-sided limits at the endpoints. Okay, so let's move on. This is a very nice example about the differentiation. Show that the absolute sign function is differentiable over this interval. You see 0 is not included in this interval, is not included, meaning that f of x equals absolute sign of x is not differentiable at x equals 0. We will try to show that. Not differentiable at x equals 0. Not differentiable means that the first derivative at the point 0 is undefined, does not exist, okay? So let's try to show this. We are searching for this. Okay, first of all, look at the graph. This is the graph of the absolute sign function. Why do we draw this graph like that? Because, okay, maybe I can put a small recall here. Normally, you draw the line y equals x like that. It's a line passing through origin. When you take the absolute sign of it, all the values of y or all the values of this function having negative images will turn to positive after you take the absolute sign, right? That's why you take the symmetry of this part on the graph. So if you do this, if you send all the negative images to the positive part like that by taking the symmetry, then you obtain the graph of the absolute sign function. So that's why we have this function for y equals absolute sign of x, okay? And look at the origin here. Let me ask you, is this function continuous at the point 0? So f of x equals absolute sign of x is in fact continuous at x equals 0. Why this happens? Because you can easily look at the limit of this function as x goes to 0, and you can check that whether it is a defined value of the function or not. You know, this is the formal definition of being continuous at a point, right? So you see that the limiting value, the result of the limit is same as the defined value, which is enough to say that this function is continuous at x equals 0. You see, all the values are approaching to 0. Defined value at the origin is defined as 0 again. That's why there is no problem about continuity. But when it comes to the differentiability, you may start having problems. Okay, this part is the part where we check continuity. Is checked like that. If I can rewrite to here quickly so that we see them after one another, continuity and differentiability. Continuity at x equals 0 is easy. You just send x to 0 and find the limit of this function at the point 0, and the defined value is the same. That's why it's continuous. F of x is continuous at x equals 0. What about differentiability? Differentiability, let's check. Differentiability at x equals 0. Okay, we can check it by applying right hand and left hand limit. Right hand derivative is computed as this one, you know. I will use this limit definition by inserting 0 for the certain point A. So if I will be looking at this limit, okay, let me write directly the limit. As h goes to 0 from right, f0 plus h minus f of 0 divided by h. This is right-hand derivative at which point? At x equals 0 point. Okay, we can easily, quickly compute this limit. What is this? Our function is absolute sine function, remember? So this is evaluated as absolute sine of h, where this is evaluated as absolute sine of 0, which is 0. That's why we have here limit as h goes to 0 from right, absolute sine of h divided by h. Since h goes to 0 from right, okay, 0 is here and we are approaching from right. That's why you can evaluate this absolute sine as it is because h is always positive. This gives you the result as 1. Now, we will do a similar computation for the left-hand derivative. Let's look at left-hand derivative at x equals 0. Okay, so limit as h goes to 0 from left of the same thing. Okay, these are all the same. This is absolute sine of it. This is 0. And we are computing the limit of the very same expression, but this time as h goes to 0 from left, meaning that you are approaching 0 by h from left like this. That's why this is negative. So absolute sine of it is computed as minus h. So the result is minus 1. As you can see, right-hand derivative and left-hand derivative are not the same. That's why you can conclude that y equals absolute sine of x function is not differentiable at the origin, which is x equals 0, okay? Is not differentiable because right and left-hand side derivatives are not the same. So here we can put a remark. If a function is continuous at a point, then this doesn't mean that it has to be differentiable there. Differentiable at x equals a. So in fact, this is not correct. This does not happen. You see, we just showed one example of this kind of phenomena, showing that if a function is continuous at a point, it may not be differentiable there. So continuity doesn't make sure the differentiability of the function. But if you consider the reverse direction like that, if a function is differentiable, then this direction holds. If a function is differentiable, it is certainly continuous at that given point. So the reverse direction is working while the direction in this side does not hold. There are functions which are continuous but not differentiable at that point. Absolute sine function is an example of that. But whenever a function is differentiable, then you are sure that your function is continuous there, because to be able to talk about differentiability, a function has to be continuous at that point, okay? So let's concentrate on this example now about the differentiability. This time we are working with the square root function, y equals square root of x. And we want to consider the derivative at the origin. So let's try to see the slopes of the tangent lines as our point approaches towards the origin, okay? You see the tangent lines are becoming more and more vertical as I move them towards the point 0. And at the origin, the tangent line becomes a vertical line. So this function has a vertical tangent at x equals 0. If a line is vertical, then what can you say about the slope of it? If you have a vertical line, the slope is infinite. And we also know that slope is the same as the first derivative of the given function. So our spatial point is 0 here. So first derivative of square root function at the point origin is in fact infinite, and this is a geometric explanation of it. It is infinite, in other words, undefined, because this function has a vertical tangent line. We can also explain this algebraically by computing things. In the upper part, we showed by using the limit definition that for the square root x, the first derivative function is 1/2 square root of x. That's why it is this expression f prime is not defined at x equals 0. If you try to insert x equals 0 here, you get the infinite value, right? F prime 0 becomes undefined infinite. This is the geometric explanation of it, and this is the algebraic explanation of it. That's why we will say that this function, square root function, is not differentiable at x equals 0 point, okay? Maybe a very quick recall for you. If a line is horizontal, at some point, if the tangent line is horizontal, then its slope is 0 for the horizontal lines. Then the slope is 0. If you have a vertical tangent line, this is a vertical line. For the vertical lines, we have infinite slopes, okay? So let's move on. And in this part now, we will try to examine and search for the cases when your function not have a derivative at a point. So these are all the bad cases where the function may not be differentiable at the given point, okay? So let's try to understand all those cases one by one. Okay, when does a function not have a derivative at a point? Look at the first case, please. Here, our graph is the one drawn with the blue. So at this point here, we have a corner type of behavior. So we have a corner. If you have a corner, your function is not differentiable there because you cannot draw a unique tangent line so that the slope is not unique. So right hand and left hand derivatives are different. F is not differentiable. So whenever you have a corner at a point, one-sided derivatives will obviously differ. That's why your function will not be differentiable. Also, similar situation occurs when you have a cusp. Cusp is a graph like that. I mean, is a behavior like this. So such points are called the cusps of your graph. And whenever you have a cusp, your function will not have, again, the first derivative there. Let me draw it here. Right at this point, again, since it is a cusp, f is not differentiable there because approaching towards this point on one side, the slopes will approach towards minus infinity, while approaching from this side, the slopes of the tangent lines will approach to plus infinity. That's why you won't have a unique finite slope there, okay? And here, since at the point P, since you have a vertical tangent, this is a tangent line which is vertical, the slope is then what? That's why the slope becomes infinite. Let's see why it becomes a vertical one. You see, starting from here, from left or right, if you draw tangent lines and approach drawing them by, I try to draw it at exactly the point B, you start obtaining a vertical tangent line. That's why the slope is infinite, and that's why your function, first derivative function, is not defined there. That's why f is not differentiable for such points where you have vertical tangents. And look at this case. In part 4, we talk about discontinuity. In the first part, the discontinuity happens because there is a jump, there is a break at your graph. There's a jump here. That's why your function is not continuous anymore at this point. So at this point, f is not continuous. If your function is not continuous, you cannot talk about the differentiability. So f is automatically not differentiable because of this jump, and this jump causes your function not continuous or not differentiable. And look at this type of discontinuity here. Okay, there is no jump, limit exists, but the limiting value is not the same as the defined value of your function. So at this point, again, f is not continuous, and which means automatically f is not differentiable again. So discontinuity may happen in these two ways, and it affects differentiability directly. If your function is not continuous, it cannot be differentiable. Okay, and the last case, the differentiability is violated by the wild oscillation. We studied on this function before in our previous lecture videos. So let me remind you, sine 1 over x function, when you multiply it with x, the graph is affected like, okay, you will again draw sine 1 over x behavior, which oscillates infinitely many times around the origin. But that if you multiply it with x, the graph can move only between y equals minus x and plus x. That's why at the origin now, it is in fact continuous. So let me show why this function is continuous at the origin. Limit as x goes to 0 of this function, this is y equals f of x, which is defined like that. So this limit by sandwich theorem is 0 because the values of your function is squeezed between x and minus x by sandwich theorem. And it is in fact the defined value of your function. You see at x equals 0, it is defined as 0. That's why it is continuous. So f of x is continuous at the origin. Even if it is continuous, the first derivative may not exist, and which is the case here. At the origin, this function is not differentiable because you cannot draw a single unique tangent line there because it behaves like doing a wide oscillation around the origin, okay? It won't be possible to draw a unique tangent line because of the wide oscillation. That's why your function is not differentiable at the origin where it is continuous at there, okay? So these are the 5 different cases where your function may fail to have a first derivative, okay? So these cases are important. Okay, the last thing that I want to tell you in this lecture video is this thing. If your function is differentiable, has a derivative at a point, it has to be continuous there. So In fact, I already covered this as a remark above. Let me write it once more and I will stop. If f is differentiable, this is enough to conclude that f is continuous, but the reverse direction doesn't hold, meaning that there are functions who are continuous but may fail to have first derivative there. What is the example of showing that the reverse direction does not hold? We covered this example, right? Absolute sine of x, remember? So this function at the origin, f of x, absolute sine of x, this is continuous at x equals 0, while it is not differentiable at the origin, okay? It fails to have a differential first derivative there because there is a corner. That's why first derivative does not exist there. At corners, remember, our function fails to have first derivative. So if differentiable, then for sure it is continuous. But there are functions who are continuous at point, but fails to have first derivative there, okay? Differentiability implies continuity, but continuity does not imply differentiability. So that's the last part for today's lecture video. I stop here. Thank you for listening. See you in the next lecture video.